our discussion of the derivative of an impulse. Right? If you recall, in the previous lecture, we had asked the question, what happens to the impulse on being passed through a differentiator? And the question was relevant because we said the impulse response characterizes a system which is linear and shift invariant completely, and therefore, if we understood, if we appreciate that a differentiator is a linear shift invariant system, then we must be able to either characterize its impulse or say something to be able to fulfill this, property of LSI systems. Now, to that objective, let us look at how we constructed the impulse, also bring in variations on how we can construct the impulse in the first place. Yeah? See, we constructed the impulse looking at the limit of the following pattern. We said we have a function, well defined but discontinuous function, which is 1 by delta, which has a height of 1 by delta, or interval of delta. Right? That interval of delta could be either located symmetrically on both sides of 0, it could be on one side of 0. In any case, all that would finally, when as you look at the limit of this kind of object as delta tends to 0, we finally lead to an object which encloses a unit area in 0 length, 0 space. Right? So, the whole idea in an impulse is to be able to enclose non-zero area in 0 space. Right? Now, the problem with that is that, you see, there are issues about uniqueness here. For example, suppose I took the following function. I took a function which overall had an area of 1. So you take a triangle with an area of 1 and which is between two limits. You need not, of course, the area of the triangle is the base multiplied by the height divided by 2. Right? So you would then need to have the triangle going from minus delta to plus delta, of course, with a height of 1 by delta, right, which would lead you to an area of 1 again. Right? So, naturally the question is, suppose in this object, if I investigate, does it lead me to a different kind of mathematical object? Does it lead me to the same mathematical object? Yeah? And now, having constructed this variation, there are so many other variations that one can construct. I mean, this need not be linear. It could be some other polynomial. Need not be polynomial at all. It could, for example, be 2 little pieces of an exponential. In fact, the worst part is it need not have a finite support or a compact support at all. You might visualize a situation where you have 2 exponentials like this, decaying in both directions. And then it is naturally important to ask whether, you definitely lead down to the same impulse. I mean, if you try to match, if you try to arrange the height of these exponentials in such a way that the total area enclosed is 1, then again the question arises, is the object that this leads to different from the object that this leads to, and so on. Now, that is the place where we need to intervene and make a remark. It turns out that all these limiting situations bring you to the same mathematical object, namely the unit impulse. So it does not matter whether you start with a piecewise constant function like this, or you start with 2 pieces of linear functions like this, or you start with 2 pieces of an exponential, and so on. They all finally lead you to the unit impulse. And that's what makes the unit impulse so universal in its character. In fact, that's also what gives us so much of flexibility and variety in determining the impulse response. So, for example, if it is convenient to me, I might look at the response of the system to this input and find out the output as delta tends towards 0, or I might do it for this, or I might do it for this, whichever is convenient to me. And if the system has a well defined impulse response, all of them should lead me to the same result. They may lead along different paths, that is, the actual functions that result, the actual responses to each of these would be different as expected, but they would have a parameter in them dependent on delta, and as that parameter tends towards 0, as the parameter varies with delta tending to 0, all those functions will ultimately converge towards the impulse response. Alright, that is what we mean by having just one object, unit impulse. This is a point to be emphasized because it also leads us to the next question: how do I find the derivative of an impulse? Right? I must also, if I wish to find, or if I wish to visualize the derivative of an impulse, I must do it by a procedure very similar to what I did for the impulse itself. So I should be, for example, able, so the principle here is, if I wish to find the impulse response of a differentiator, then I should be able to find the response of the differentiator to each of these individual inputs, and then take the limit as delta tends towards 0 for each of them in turn. Yeah? So let us take the limit for each of them. Let us take each of them in turn. Let us take this one first. So what kind of a derivative does this have? You see here, of course, the moment you have a discontinuity, we have agreed that the derivative must have impulses. So here we will have a situation like this. There is going to be a positive impulse, right? See, because the situation is that, you know, the function is 0 up to this point and then suddenly rises to 1 by delta. So if you take a running integral of the derivative, it should give you back the original function. So in the running integral, there must be an impulse which contributes an area of 1 by delta, right? So you must have here an impulse of 1 by delta in the derivative. A positive impulse of 1 by delta. And when you reach this point, suddenly the area, the total running integral drops from 1 by delta down to 0. So therefore, there must be an impulse there which contributes an area of minus 1 by delta. There we are. So here we have an impulse of strength minus 1 by delta. At delta by 2. And now, what is the situation? We have two impulses of strength respectively plus 1 by delta and minus 1 by delta, spaced with a spacing of delta. Now, as delta tends to 0, we have two issues of trouble. One issue is that the two impulses start coming arbitrarily close. So it seems as if the impulses should overlap, but they don't really, you see. The other issue is that, see, not only is the impulse troublesome to our minds, because it encloses non-zero area in 0 length, but now we have another trouble to work with, namely that the area itself starts blowing up as delta tends towards 0. So now we have to deal with two pieces of trouble. One is that you have two objects that contribute an infinitely growing area, but, you know, contradictory to one another. So, you know, if one of the areas is positive, the other is equally negative. And the second is that these start coming arbitrarily close. And this is the object that we must visualize when we talk about the derivative of an impulse. Again, naturally, needless to say, the impulse itself violated certain norms about a function. This object, whatever it is, violates them even further, right? In fact, this object we shall call a doublet or a unit doublet. unit doublet to denote the fact that this is a unit derivative, I mean dxt dt, right, not 3 times dxt dt. That is why unit doublet. And doublet because you have 2 impulses. So, it is not simply 2 impulses, it is 2 impulsive impulses, impulses that start growing towards infinity, each of them separately, and start coming arbitrarily close. Now, in fact, let us look at what happens to the other functions that we were dealing with, which also moved towards the impulse. So, for example, suppose we considered the function given by the triangle here. Let us look at the derivative of this function. In this side, the derivative is positive and has a slope of 1 and has a value of 1, right? Well, not quite 1, it rises to 1 by delta in the interval of delta, right. So, 1 by delta squared. And here it has a negative slope of the same value, minus 1 by delta squared. So, what here? You see, you have a flat function, you have a pulse of height 1 by delta squared with a width of delta here, I mean from minus delta to 0. So, the area enclosed here is 1 by delta, and the area enclosed here is minus 1 by delta. Yeah? So, now again we can liken it to the earlier discussion. As delta tends to 0, what happens? Well, this takes you to an impulse of strength delta, and this takes you to an impulse of strength minus 1 by delta. So, again you have 2 impulses, both of strength 1 by delta, and the spacing starts reducing arbitrarily towards a small value. Yeah? And therefore, as you can see, even this, since both, as expected, since both of these objects, both of these functions start converging to the same object, the unit impulse, their derivatives also converge to the same mathematical object, namely unit doublet. This also converges to the unit doublet as delta tends towards 0. Now, I leave it to you as an exercise to take other examples. For example, the double exponential. Look at the derivative of the double exponential, properly scaled so that the area is 1, yeah, and look at its derivative as the exponential is made faster and faster, decays faster and faster, and convince yourself that all of them ultimately lead you to the same mathematical object, which is difficult to characterize in the language of functions, but which can be characterized by its behavior under an integral. That is the whole beauty of this object. It has a very well defined behavior under the integral sign. What is the behavior under the integral sign? Well, let's give this object a name now. Let's give this unit doublet a name. In fact, let's give this whole class of objects a name. We'll call the unit step, we called the unit step ut, right? We shall now call it u1t. For reasons we'll understand shortly. Or well, maybe u minus 1. Let me use minus 1 for the moment. I mean, to be consistent with a lot of literature. One can use 1 or minus 1, but one use minus 1. Let's call delta t, which is the unit impulse, let's refer to it by u0t. And then we shall have a name for the unit doublet. We'll call it u1t. And now we see a pattern. The pattern is that as you move this way, you are carrying out a running integral. And as you move this way, you are carrying out a derivative. Of course, you must interpret the integral as a running integral. Running integral means an integral from minus infinity up to the time in question. Derivative, of course, doesn't need explanation. Derivative is a local operation. Yes? So naturally, it occurs to us that we may extend this set. So we move upwards and we may move downwards. Let's first move upwards, because that's easier to understand from our experience of mathematics at the moment. Right? So when we move upwards, for example, if we make a running integral on the unit step, what do we get? What do we get? Yeah, that's what.
So you get TUT, sir.
TUT, very good. What, and in fact, so let's work it out. So how would we get, in fact, what should we call it? We should call it u2 of t. Is that right? We should call it u minus 2. So you know, actually the idea negative denotes, see that the integer there is an indication of differentiation. So 1 means one's derivative, 2 means 2 times derivative, and therefore minus 1 means a minus 1 derivative, which means an integral. The negative derivative is an integral, right? So u minus 2t is equal to integral u minus 1 lambda, d lambda, from minus infinity to t, which gives you, as Samir says, t times u minus 1t. Now in future also, as we've been doing until now, when we simply write u of t, we shall understand it to mean u minus 1t, not u0t. Right? So be wary of this. In future, when we write simply ut, we shall understand it to mean u minus 1t and not u0t. Right? The unit step, as we've been doing in the past. And in fact, now on the upward direction, it is far easier to characterize these. In fact, they are all functions. Let's sketch u minus 2t. How does it look? U minus 2t has an appearance like this. This is u minus 2t. It is linear. Yeah? And we can find out u minus 3t. In fact, we can find out u minus kt. And we shall prove by mathematical induction, or we shall obtain u minus k by mathematical induction. So let's see a pattern, then we can put down the inductive expression. So we can see that u minus 3t shall be integral lambda d lambda from 0 to t. This one multiplied by u minus 1t. Is that right? U minus 3t shall be lambda d lambda integrated from 0 to t. That's essentially u minus 2t integrated from minus infinity to t. And this gives us lambda squared by 2. So t squared by 2 times u minus 1t. And now we notice that every time I carry out integral, you shall be increasing the power of this by 1 and you shall be dividing by the next integer. So it leads us to an expression for u minus k. U of minus kt for k positive. Now this denotes the set of positive integers. All right? Is equal to t raised to the power k minus 1 divided by k minus 1 factorial times u minus 1t. To take an example, u minus 2t is just, so 2, that's t times u minus 1t. All right? So we can prove. So I leave it to you exercise to prove by mathematical induction. So this is so much so for the positive side or the upward side. What about the negative side? That is troublesome. In fact, at every step we are going to have trouble, because every time we go one step downwards in the hierarchy, we encounter one more cause of trouble. When we went from u0 to u1, the cause of trouble was that you had two impulses coming arbitrarily close, each of them growing without bound. Now let's see what happens with the second derivative to get an idea. So let's look at u2 of t. And naturally, to look at u2 of t, we will not be able to take the concept of two impulses. Rather, we'll have to start by one of the other functions that will lead us to a function on taking the derivative. So we'll have to start with the triangle to begin with. It would not help us to start with the two impulses. So let's start with the triangle. This is I'll say an unprocessed or a raw u0t. We'll write down the corresponding raw u1t. So this is a raw U1t. And now we can take a raw, so here we can have a raw U2t, right? What will the raw U2t look like? Well, we take the derivative of this. So what will the derivative look like? Well, here you suddenly need to put in an area of 1 by delta squared, right? So you will have a positive impulse of strength 1 by delta squared here. At minus delta. And at 0, you suddenly need to put in a negative area of 2 by delta squared. So what I'll do is I won't keep drawing them above and below. All right, let me do that. No harm. So don't worry about the scale. I'm not drawing it to scale. So minus 2 by delta squared here at 0. And at plus delta, it will again put in an area of 1 by delta squared to close the function. So now what is the problem? Now we have 3 impulses, right, of strengths respectively 1 by delta squared, minus 2 by delta squared, and 1 by delta squared located at minus delta, 0 and delta. So as delta becomes smaller and smaller, what happens? Each of these impulses, of course, starts growing in strength without bound. But not just that, it's, the rate at which they grow is now squared, 1 by delta squared. And of course, needless to say, they start coming closer to one another too. So now you have 3 impulses coming closer to one another, each of them encompassing an infinitely growing area, and the growth is as the square of the original one. So this process can be now continued. Now we get a feel of these objects, right? So the impulse response of a double differentiator is a limiting situation of this case. So whatever object you get when you visualize going towards 0, when you visualize delta going towards 0 here, is the object that you get giving you the impulse response of a double differentiator. And similarly, one can have an impulse response of a third order differentiator, a fourth order differentiator, and so on. Yes, Subhen. Yes. There's a question. Just quickly pass it to. Yeah. Have a. Yes. Yeah. All right. Well, the question is whether this strength should be 1 by delta and not 1 by delta squared. Now, how should we determine the strength? See, when you have a strength of 1, it means it feeds in an area. It's like a sudden shot in the arm. It feeds an area of 1 suddenly as you integrate. So, that means a function jumps by a value of 1 when you have a strength of 1. So here you notice the function suddenly jumps by 1 by delta squared. So you need to have a shot in the arm of strength 1 by delta squared. Right? So, and here you need to have a shot in the arm of strength minus 2 by delta squared to jump from 1 by delta squared minus 1 by delta squared, and so on. So therefore, the strength should be 1 by delta squared. In fact, this is also in consonance with our understanding that as you go towards higher and higher orders of the doublet, or as you go towards the impulse response of higher and higher order derivatives, you land up with more and more trouble in the strength of the impulse. The strength of the impulse starts growing even more in a troublesome manner without bounds. So, these objects, at least the unit impulse, can be visualized to an extent by us. we can visualize it. It captures the unit area and so on. But when you go to the doublet, it's even more difficult to visualize. There are so many things that we have to encapsulate in our understanding of the doublet. But we'll get used to it. But you see, as I said, we don't really need to worry too much about the nature of a doublet. That's just for our understanding, or for that matter. So if we like, we can call this a unit triplet. That's up to us. There is no standard name, and one can keep giving names accordingly. But that's immaterial. It is so much more sensible to call it U minus U2 and U3 and so on. Yeah. So in general, UKT understood this way is the impulse response of a kth order differentiator. Now you see, we need to understand what we mean by the behavior of these objects under an integral sign. So we've already seen the shifting property of an impulse. We've already seen what happens when you take a function, let's say xt, and multiply it by delta t minus tau. If xt is continuous at tau, then this is equivalent to x at tau multiplied by delta t minus tau. It's equivalent. One must write equivalent there, right? And if we integrate both sides with respect to t, we've seen this earlier, this gives us x at, well, you see, it's a tricky thing here. I'm sorry, yeah, with respect to tau. Well, now here you need to see there are, all right, we have a choice whether we wish to integrate with respect to t or with respect to tau, right? Now if you choose tau as a fixed number, right, then if you integrate with respect to t here, what would you get? You would simply get x of tau, right? Because this could come out, you see. And similarly, we can write down some behavioral patterns related to the unit doublet. For example, what happens when we multiply a function xt by a unit doublet? So let's call it u1, located at tau, and integrate with respect to t. What would this do? This would essentially pick up the derivative of the function at t equal to tau. So this would give us dxt dt evaluated at t equal to tau. That's all right. The derivative of xt, right? No, not multiple. The question is whether there should be a product. No, there is no product of delta t here. See, we've already integrated. I mean, take the analogous case if you took u0 here and you integrate. What have you done when you integrate? See, I mean, what is this object doing really? If you think about what is this object doing? This unit doublet is picking up xt at the points, at 2 points very near tau. taking their difference, dividing by delta, and taking the limit as delta tends to 0. That's essentially calculating the derivative at t equal to tau. So, if you look at it, that way the unit doublet makes a lot of sense. See, what does the unit doublet do? It picks up the function at 2 points very close to one another, so it takes the difference between them and divides by the interval, and then takes the limit of this as delta tends to 0. That's essentially the derivative. So, therefore, this would pick up the value of the derivative, if it exists, at t equal to tau. So, needless to say, here you assume that the derivative must be continuous at that point. Yes, Nirmesh, yes, yeah. At all points? At all points 0 then. If xt is 1 for all t, then this would give you a value of 0 at that point. So, it would, the doublet would pick up 1 and 1. Be careful. You see, alright, good. Now, here comes an important question. It's a very pertinent question that has been raised, right? I can have a number of functions that are all constant. There's an infinity of functions that are all constant, right? As a function of time. And if I take the derivative of this, they would all give me the 0 function. There is a problem here. Right? It really means that, when you have a function that is all constant, and if you apply a unit doublet on it, it's a singular process. Singular means, there are many different functions that give you the same answer, so it's not invertible. So Nirmesh has brought out a very important point in the context of doublets. When we try and apply a running integral on an all 0 function, it seems to lead to an all 0 function. But if you happen to have a function which is constant for all positive, or starting from some point onwards, then of course the doublet, when operated on this, would give you an impulse at this point, and then there would be no trouble, because if you took the running integral, you would get back the original constant correctly. So here, in fact, we run into a problem related to these objects that we've been talking about. And in fact, I'm very glad this point was brought up, because that is the motivation for the name singularity functions. They are called singularity functions. These objects, the UKTs, the UKTs are called singularity functions. Singularity refers to the fact that, you can have a situation where something vanishes. That's what singularity means informally in mathematics. Sometimes a differential equation has a singular solution. A singular solution is a solution which you may not be able to obtain by a systematic procedure. It satisfies the equation, but it is not obtained by a systematic procedure, by the procedure that is normally used to solve a differential equation. So in fact these objects, so in fact as you know, as you look at these objects, so what it really indicates is that these objects are indeed quite mysterious in many ways, right? There are subtle points about these objects that don't present themselves at first glance. This is one of them, right? That you know, if you look at the unit doublet, when it operates on a function that is constant after a point in time, it behaves correctly. But if it operates on a function that is constant for time, then there is this problem of non-uniqueness when you go the other way. So it's not quite inverted by applying a running integral, right? So in fact, maybe we won't really explain entirely why this problem comes up at this stage. It's a little beyond the scope of this course, right? It's a little beyond the scope of a first discussion on such objects. So we won't take this issue up further except to recognize that you know there are these so-called singularity issues, and that's the reason why these functions are called singularity functions. In fact, as I said, the word function itself is a misnomer. It's not a function. So much so then for singularity functions. And we proceed then to the last issue that we wish to discuss in the context of time domain analysis directly, or direct domain analysis, whether time or space. What do I mean by direct domain analysis? I mean that you are analyzing the system or the signal in the very domain in which it is defined. If a signal is defined in time, you are analyzing it in time. If a signal, and therefore the system operates in time, so you are analyzing it in time. If the system is defined in frequency, well, we don't know what do you mean by defined in frequency. So at this moment, if it's defined in space, we are analyzing it in space. So it's called same domain analysis of the system or the signal. So this is the last issue that we shall now deal with in that context. The last issue relates to a very important class of linear shift invariant systems that you know we normally encounter in most branches of engineering and science. Namely, in the case of continuous time or space, it's a class of systems defined by differential equations. The idea is this. You see, the derivative operator is a linear shift invariant system. We've already seen that a cascade of linear shift invariant systems is also a linear shift invariant system. So multiple order differentiator is also a linear shift invariant system. So we could have and then we've also seen, so cascade of LSI systems is an LSI system. A parallel combination of LSI systems is again an LSI system because of the distributivity of convolution. So therefore we could visualize a system like this. We could visualize a system where you have the input being subjected to successive differentiation. And we take a linear combination of these. And the linear combination gives you the output. This is one very important class of differential of LSI system, linear shift invariant system. It is very clear that these systems are LSI, right? And what is the corresponding case for discrete time systems? Well, let us come to that also. There we need to replace the differentiator. But there is a further improvisation that we can make here. See, here the output is explicitly expressed in terms of the input. But we may have an implicit relationship. That means we may have a situation where the derivatives of the output and a linear combination of the derivatives of the output are equal to a linear combination of the derivatives of the input. Right? So, we may have a situation like this. We may have for example 3 times the second derivative of the output plus 2 times the second derivative or the first derivative of the output plus the output itself is say 5 times the third derivative of the input, and so on. This could be an example of an implicit description. So, here the idea is that you have these linear shift invariant operations acting on the output and on the input, and a certain set of linear shift invariant acting on the output is related to a set of linear shift invariant operations acting upon the input. This is the kind of system that we very often encounter in a lot of branches of engineering and science. Whether in electrical engineering, for example, in the context of electrical networks, this kind of a situation is encountered very frequently. In the context of devices, electromagnetic devices, we encounter this situation very, very frequently. We also encounter this in mechanical systems, where you have equations of mass, of springs. We encounter this in the context of fluid flows, or heat flow, or thermal behavior of systems. We encounter this in the context of, for example, other processes like textile processes or other manufacturing processes. These equations are also encountered in biomedical situations to describe the evolution of biological systems in science, in physics. They are useful in the description of the universe in astrophysics. So, there is a wide, of course, we appreciate the importance of differential equations, but in particular of what are called linear constant coefficient differential equations, which constitutes this. These are called linear constant coefficient differential equations. Are an important class of differential equations. The terms linear, of course, refers to the fact that there is a linear combination. Constant coefficient refers to the coefficients of the derivative, right? And that's the explanation of the term. Now, what is the corresponding situation in discrete time? In discrete time, we have a differential operator, but we have a operator which serves like a derivative operator. So, in discrete time, the situation follows. You have the sequence xn. We successively delay the sequence by one sample at a time. So, we lead to xn minus 1, xn minus 2, xn minus 3, and so on. We will denote the operator by delay or d, by one sample, by one unit of time. and so on. And therefore, what results here is xn minus 1. At the next step, it shall be xn minus 2, and so on here. And therefore, a general class of equations describing a linear shift in one very important, not the most general, but a very important class of linear shift invariant systems in this time are described by an equation of the form yn is summation, say k going from 1 to n, some constant coefficients times delayed versions of the output plus so we have output at the current instant related to a linear combination of past outputs. By past outputs, I mean outputs obtained as a linear combination of past values of y, right, plus a linear combination of the current input and some past inputs. Now, this class of equations which are in discrete variables is called the class of linear constant coefficient difference equations. The difference is only in the word difference. So, as a mnemonic, both in the continuous variable case and also in the discrete variable case, we have the class of LCC DEs. Linear constant coefficient, either differential equations for the continuous variable case or difference equations for the discrete variable case. Difference, we mean these kind of operations where we delay and take a linear combination. Yeah? Yes, there's a question. I mean, yes.
Sir, in this equation, we are relating yn to previous yns outputs, but each yn, like there will be at least one yn which is totally dependent on x's. So we can represent yn as linear combination of only the inputs. Why do we need outputs?
Good. All right. So the question is, do we need to bring in past values of the output? Let me give you an example to illustrate both the yes and the no part of the answer. Let's take the very simple difference equation with yn is y of n minus 1 plus xn. All right. Now, this might be, you can rewrite this by saying this is also equal to, from the same equation, yn minus 1 will be equal to yn minus 2 plus xn. You might write this as yn minus 2 plus xn minus 1 plus xn. And this process can be continued. So, you may write this as yn minus, say, L plus xn minus L plus 1 and so on plus xn. And one can argue that one can go infinitely backward in time until one reaches a zero value of y. Perfectly acceptable, an idea. perfectly acceptable as an idea. Now here, this is a very important point that has been raised because it brings up another issue in systems. See, we can go back to a point in time which supposedly has, so if you go back to minus infinity, hopefully we should reach a zero value. But what are we saying then? The system has an infinite length description. The description of the system requires an infinite amount of resource. Or if you try and implement this equation on a computer, you will require an infinite number of calculations for every possible n. So the beauty is that the same system which seems to require an infinite amount of calculation can be captured in a finite amount of calculation if we include the output in the description or the passed output in the description. So sometimes the inclusion of the passed output in the description serves to make the system realizable. So we need to bring in the concept of realizability here, which we haven't brought in so far. We'll use a very succinct definition of realizability. What do you mean when you say a system is realizable? A system is realizable if for every value of the independent variable at the output, there is a finite amount of resource that needs to be invested to obtain that output from the inputs or past or other outputs. So finite amount of resource requirement, finite, whether computational, hardware or whatever. Whatever resource, we don't mind, but all resources, finite computational, hardware, etc. resources for finite amount of output calculation or for calculation of the output in a finite time. By finite output calculation, what I mean? Calculation of the output over a finite range of the independent variable at the output, right? So if you have a finite range of the independent variable at the output, the amount of resource that you need to invest to obtain that output in the realization of the system must be finite. Then you say the system is realizable. So in fact, there are many LSI systems that are not realizable, or at least whose realization is not known to date. We can approximate them, but we cannot realize them exactly. That's the paradox of LSI systems. In fact, there is a much worse paradox, which I would like to bring to your notice at this stage. You will probably realize it more as you go along, not only in this course, but maybe even in your study of electrical engineering or any other branch of engineering. The ideal systems that we for in situations are unrealizable. And that's why design is an issue. You see, it may seem philosophical, but it's a very, very practical statement. Most engineering branches have unrealizable physical idealizations. And engineering design is both an art and a science, because one needs to do as well as one can with realizable systems to realize the unrealizable, or to go as close to the unrealizable as one can get. To take an example, electrical filters. Ideal filters are unrealizable. But with realizable filters, one can go as close as you like by designing them properly. And that's why filter design is an art. Right? So with that, we shall then conclude our discussion of linear shift invariant systems or systems in the domain of analysis, and proceed from here the next time.
Firstly, sir,
Just a moment. Now please remember, on Monday you will be